1,6-diphosphate. So that now brings up reaction number 4. Reaction number 4 involves an enzyme called aldolase. It is written right there, right there. I'm not sure if you can read it or not. Aldolase. Now this one will be a little more tricky because the first two enzymes were very specific. They transfer phosphate, they change the shape of the molecule. Not quite so clear with, or specific with aldolase. Aldolase breaks the 6-carbon molecule down the middle. See, it is still a fructose molecule. You still got 6 carbons. So you're breaking, or aldolase is breaking it right down the middle into 2 separate 3-carbon molecules. That's why down the middle. So here's 6 carbons, and now you've got 2 separate molecules, each with 3 carbons. That's what aldolase does. And notice each of these molecules has a phosphate. I think you may, on your chart, you have a little bit cut off, but CH2O and then a phosphate is right there, and another phosphate, gives a sort goes down below here. It may have gotten cut off a little on your chart. You might just throw that in. But this was the reason for the third reaction, that second phosphorylation reaction, where we needed phosphate on each side. Because now with aldolase, breaking it down the middle, each of these 2 molecules has a phosphate on it. That's why we needed symmetry. 3-carbon molecule. There's 3, there's 3. And each one has a phosphate. You don't need to remember the names. By the way, you don't need to know the structures. That would be just death. You don't need to know the structures. Yeah?
So are both of those the same equation?
No. They are different. This is, well, the names, dihydroxyacetone phosphate, glucosaldehyde 3-phosphate. The difference is right there. You can't tell by looking at it. The CHO is actually that. It's a carbonyl plus a hydrogen. That's CHO. So what these 2 molecules are is in this top molecule, the carbonyl is in the middle. On the bottom molecule, glyceraldehyde, the carbonyl is on the top carbon. So they are different. The reason they're different is because the oxygen here with the fructose, that oxygen has to go to one side or the other. There's only one oxygen. It can't go to both. And that's why, I'm sorry. Actually, it goes to the one here. But don't worry, it's not too much detail. I was going to say here. That's why I was very, very careful when I was saying the enzyme breaks the molecule down the middle. I did not say it breaks the molecule in half. See, that's a different comment. Breaking a molecule in half means you end up with 2 halves. 2 halves that are equal. Exactly. They're not equal. So that's why, again, I was very careful to say breaks the molecule down the middle, splits the molecule, anything like that. But don't say splits it into half, because that's not correct. That oxygen there can only go to one side or the other. And therefore, you do get 2 different molecules.
Okay. So do you want us to just know the 2 different names?
Not really, because of the 5th reaction. So for right now, bear with me, but I'm going to answer your question in a couple minutes. So right now, we have 2 different molecules, each with 3 carbons. She was asking if you need to know both, but I didn't want to answer. I will in a little bit. Now, I want to stick with aldolase for a second. This actually is the first significant reaction. Now, you might wonder, what do you mean significant? What the hell have we been doing for 45 minutes? Actually screwing around, believe it or not. I know you've had more fun doing other stuff, but the thing is, if you just look at fructose 1,6-diphosphate, there's not that much difference from the original glucose. it wouldn't take that much effort to go backwards. All we've really done is added a couple phosphates, and we moved an oxygen bond. That's all we've done. It wouldn't take that much effort to go backwards. However, now with the autolysis reaction, you can see that these two look completely different than the original glucose. Basically, the autolysis reaction is the point of no return. Once you've done the autolysis reaction, it becomes extremely difficult to go backwards. So there are two reasons why this is the first significant reaction. The first reason is what I just told you, that it represents the point of no return. Once you go beyond that, then you're kind of committed. You got to keep going.
And the autolysis is the fourth reaction, correct?
Yes.
Okay.
The autolysis reaction is the fourth reaction. The fourth reaction is producing this and this, producing those two separate 3-carbon molecules. That's the fourth reaction. Now the second reason, this is the first significant reaction, is because it's the first time we've broken a carbon-carbon bond. The carbon-carbon bond is going to be right there. We're breaking the bond between these two carbons. Be 1, 2, 3, 1, 2, 3. So we're breaking a carbon-carbon bond. That may not mean much to you, but let me remind you of something. That we are doing respiration. We are going to break down glucose to produce carbon dioxide. That's what we exhale. Well, 6 carbons, 6 carbon dioxides. We have to break every single bond. That's what we're going to be doing, is breaking every single bond. This is the first time we've done that. So again, that's the second reason why it's the first significant reaction. So point of no return, and second, first time we've broken a carbon-carbon bond. So autolysis is a big deal.
Can you say that again?
Yeah, it's the first significant reaction for 2 reasons. One is the point of no return. Once you've broken that molecule, the fructose, into 2 separate 3-carbon molecules, you really can't go back. I'm sure you could, but it's really unlikely. Second, it's the first time we've broken a carbon-carbon bond. Remember, ultimately, we have to break all those bonds. This is the first time we've done it. So again, autolysis represents the first significant reaction. Everything else was just window dressing, screwing around. Okay, the 5th reaction, and this would now be the answer to your question that I put you on hold for. You have to do something on your chart. Please draw an arrow from this top molecule here, pointing to the second molecule. The top molecule is dihydroxy acetone phosphate. The second molecule is glyceraldehyde 3-phosphate. So please draw an arrow from the acetone down to the aldehyde. The 5th reaction is that the top molecule changes into the second molecule. The top molecule changes into the second one.
Is there a name for that?
For the type of reaction?
Yeah.
No. I mean, really, the only name we have is phosphorylation. None of the rest of the reactions have names. So at the end of the 5th reaction, we now have 2 glyceraldehyde 3-phosphates. We already had one from the autolysis reaction. We already had one, and now we change the acetone into aldehyde. So now we have 2. Pardon me? No, because remember, you've got your double bonded oxygen, double bonded oxygen. All you're doing is moving the double bond from the middle carbon to the one down here. That's all you're doing is moving the double bond. So no, you're not adding anything. Okay,
So
so
is that how
of the
you get
three
these
enzymes
two?
we've done so far, which one is most likely to be doing that fifth reaction? Which enzyme? Which enzyme? It would be
Yeah,
isomerase. Exactly.
Isomerase.
It would be isomerase. Isomerase changes the shape of molecules. In this case, it's moving the carbonyl, although you really don't need to worry about that, but that is what it's doing. But more to the point, kinase transfers phosphate groups. That's not going on here. And autolase specifically does that reaction. So that's not going on here. We've already used autolase. That leaves isomerase. Isomerase changes the shape of molecules. In this case, the carbonyl group is moving. That's the one here. It's moving down to here. So we end up with 2 glyceraldehydes, 3 phosphate. So at the end of 5 reactions, we've had 2 kinase reactions, 2 isomerase reactions, and 1 autolase reaction. Those are our 5 reactions. The kinase reactions are phosphorylation. The other ones don't have names. It's just reaction. So at the end of the 5th reaction, we have changed glucose into 2 glyceraldehyde 3-phosphates.
It only shows one on there.
I'm sorry.
It only shows one on the sheet, but we just.
No, I know. That's why I had you draw an arrow
Okay,
from the top one to the second one.
okay,
Because the top one is changing into the second one.
okay,
That's your second glyceraldehyde.
okay.
You're right, it doesn't show it. I don't know why it doesn't. I like the chart, but it does leave out a few things like that.
Yeah.